Picture this: a solid metal projectile screaming through the air at 7 times the speed of sound. No gunpowder, no explosives, just pure electromagnetic force blasting a 23-pound slug to more than 5,000 miles per hour. It sounds like science fiction, but the U.S. Navy actually spent 15 years and over $500 million trying to turn this into the future of naval warfare. This weapon was supposed to change everything, and yet today the program is dead, canceled, abandoned, buried. So what happened to the railgun that was meant to rewrite the rules of war? A railgun isn't a normal weapon. Forget gunpowder, explosions, or traditional barrels. A railgun uses pure electricity to fire a projectile at Mach 7 over 5,000 miles per hour. The design is deceptively simple. 2 long, parallel metal rails run a massive electric current through them, and they generate an enormous magnetic force. Place a conductive projectile called an armature between the rails, and that magnetic force launches it down the barrel at hypersonic speed. No explosives, no propellant, just raw electromagnetic power at full performance. A railgun shot can travel more than 100 nautical miles and still hit its target at Mach 5. At those speeds, you don't need a warhead. The kinetic energy alone is devastating. To put it into perspective, 1 megajoule of energy is like getting hit by a multi-ton truck moving 160 miles per hour. A Navy railgun shot delivers several times that. This is why the railgun was supposed to be the future of long-range naval firepower. To understand how a railgun fires, you only need one piece of physics: the Lorentz force. Here's how it works. A massive electric current travels up one rail, crosses through the armature holding the projectile, and returns down the other rail. That flow of electricity creates powerful magnetic fields, and those magnetic fields generate the force that launches the projectile forward at hypersonic speed. Think of the energy involved. 1 megajoule is like a 1-ton car hitting you at 100 miles per hour. Now scale that up to 32 megajoules, roughly the blast energy of nearly 5 kilograms of C4. That's the kind of power the Navy railgun was pushing through 2 metal rails. The early tests were astonishing. In 2008, the Navy fired a projectile at 10.6 megajoules over 2,500 meters per second. By 2010, they broke the world record with a 3.3 megajoule shot. But there was a massive problem. To fire at operational speed, around 10 to 12 rounds per minute, a railgun needs 30 megawatts of electrical power. That's enough electricity to run a small town. And that power requirement would become one of the weapon's biggest downfalls. The U.S. Navy officially launched its electromagnetic railgun program in 2005 with one bold objective: build a ship-mounted weapon that could fire farther than any naval gun in history without a single ounce of explosive. To make it happen, the Navy partnered with BAE Systems and General Atomics, each developing competing prototypes. In 2012, BAE delivered its 32 megajoule railgun to the Naval Surface Warfare Center in Dahlgren, Virginia, the most powerful electromagnetic launcher ever built at the time. The vision was revolutionary. A railgun-equipped ship could hit targets 50 to 100 nautical miles away, support troops on land, destroy enemy ships at extreme range, and even intercept incoming missiles, all using sheer kinetic energy instead of explosive warheads. By 2017, things finally seemed to be moving forward. Battle lie had increased from just a few dozen shots to over 400, with a long-term goal of 1,000. Engineers were preparing for Phase 2, rapid-fire capability. The aim was a weapon firing 6 to 12 rounds per minute, each shot delivering 20 to 32 megajoules of energy. On paper, the railgun was getting close to operational reality. But behind the scenes, the program was already starting to crack. Then, reality hit. After more than a decade of development, hundreds of tests, and over $500 million in funding, the electromagnetic railgun ran into problems no amount of optimism could fix. First, the barrel. The moment the Navy started firing at full power, the limitations became obvious. The rails made to guide a projectile moving faster than Mach 7 were literally tearing themselves apart. Normal naval cannon barrels can fire around 600 rounds before needing refurbishment, sometimes less than 30 before cracking, melting, or warping. Defense analyst Norman Friedman put it simply: the railgun was destroying itself with every shot. And he wasn't exaggerating. The combination of megampere electrical currents, extreme magnetic pressure, and violent heat was eroding the rails at incredible speed. Every shot was like firing a miniature lightning bolt. Second, the power problem. To operate, the railgun needed colossal amounts of energy, dozens of megawatts. Only 3 ships in the entire Navidad-Humboldt-class destroyers could realistically supply the power required. Every other ship, not even close. Third, rate of fire. Even when the gun did work, it needed time to recharge its capacitors. That meant slow firing too, slow for missile defense, the very mission the Navy hoped it would excel at, and a gun that fires slowly can't intercept supersonic threats. Fourth, the range dilemma. Yes, the railgun could theoretically hit targets 100+ nautical miles away, but although the fire ship had to move close to enemy territory well within the kill zone of modern anti-ship missiles. So the weapon extended the Navy's reach while exposing the ship to more danger. By July 2021, the verdict was official. The Navy canceled the electromagnetic railgun program. The reasons sounded clinical on paper: fiscal constraints, integration challenges, unresolved engineering issues. But the truth was simple. The railgun was a revolutionary idea that couldn't escape the laws of physics, at least not yet. The cancellation of the railgun didn't mark the end of the idea, far from it. Instead, it shifted the Navy's attention toward technologies that could deliver results right now. Entered the hypervelocity projectile, the HVP. Originally designed as ammunition for the engineers quickly realized something surprising. They didn't need the railgun at all. They could fire the HVP from existing naval guns, the standard Mk-45 5-inch gun found on dozens of U.S. Navy ships. In 2018, the USS Dewey put this to the test. It fired 20 hypervelocity projectiles using nothing more than conventional powder charges. The results were impressive. The 28-pound projectile reached ranges up to 50 miles, traveling at Mach 7.3. Not quite the blistering speeds of a railgun, but far beyond what traditional shells could ever achieve. And the advantages didn't stop there. Rate of fire up to 15 rounds per minute. Magazine depth far larger than guided missile inventories cost. Roughly $75,000 to $100,000 per round compared to $1 to $2 million per missile. Suddenly, the Navy had a weapon offering missile-like speed without missile-level expense. At the same time, the Navy began redirecting funding toward other emerging technologies. Directed energy weapons ship, mounted lasers promised near unlimited ammunition, pennies per shot, and no barrel erosion whatsoever. Hypersonic missiles offered what the railgun couldn't deliver: long-range, ultra-fast strike capability without needing the electrical infrastructure of a small power plant. They're mobile, flexible, and, crucially, deployable today. The dream of long-range, high-speed naval firepower didn't die. It simply evolved into systems that work. The railgun may be shelved in the United States, but the story is far from over. Around the world, other nations are racing to pick up where the U.S. left off. China, for example, is pushing forward aggressively. Their researchers claim major breakthroughs in electromagnetic launch technology, including a new X-shaped dual-rail design that reduces heat damage and stabilizes current flow. This system could, if their data holds, launch a 132-pound projectile at more than 5,300 miles per hour. Their goal is clear: solve the problems the US couldn't, and field the first operational railgun on the planet. Meanwhile, Japan is taking a different approach. In 2023, the test ship JS Asuka successfully fired a prototype railgun at Mach 6.5. Japan isn't just experimenting, they're developing the weapon specifically to intercept hypersonic missiles, one of the hardest defense challenges in the world. If they succeed, the railgun could become a critical shield instead of a long-range cannon. And the United States, it hasn't given up, just shifted priorities. The Navy suspended development as a shipboard gun, but officials openly admitted that technology still holds enormous potential for missile defense. If future materials solve the barrel life issue and next-generation power systems deliver the required megawatts, the railgun could return. Breakthroughs in heat-resistant composites, superconductors, and compact nuclear power are already in development. Any one of them could revive the Railgun project overnight, because the truth is simple: the physics work. The concept works. But turning a laboratory weapon into a battlefield weapon requires solving problems that $500 million still couldn't crack. For now, the railgun stands as a lesson: sometimes technology arrives before the world is ready for it. But the race isn't over, and whichever country solves the power, heat, and durability puzzle first will hold a weapon that could redefine naval warfare for the next century.